Hello everyone. Let us learn about gradient descent, which is also called as the delta rule. So this is helpful for learning the weight vector in case of a perceptron, and that too in case of non-linearly separable weights. In case of linearly separable weights, we are using the perceptron training rule. In case of non-linearly separable weights, we have to use gradient descent, which is called as the delta rule. Before getting into gradient descent, let us understand what is meant by a gradient first. A gradient is a measure which measures how much the output of a function changes if you change the inputs a little bit. For example, if you are applying brakes on a vehicle, okay, so that is the input that you are giving to your vehicle. So when you apply brakes, by how much your speed will vary. So that is the change in your output function. That is measured by the gradient. In mathematics, a gradient is a partial derivative with respect to its inputs. The same concept, mathematical concept, we are applying to the machine learning part also. So here also, we will be applying a partial derivative on the function which has more than one input variable. Okay, so this we also call as the slope of a line. So now what our gradient will measure? So our gradient measures the change in all weights with regard to the change in error. So whenever there is an error, so that means there is difference between the actual output and the observed output. So T minus O we are calculating. So this is how we calculate our error, right? So whenever there is an error, so by how much your weight should change. So that is measured by the gradient. Let us try to understand the concept of gradient descent with the help of this picture. Okay, so let us take a person who wants to climb this mountain. Okay, so climbing is nothing but he is ascending a mountain. So when the task is to get down from this mountain, the task is descending, right? In mathematics also we have ascending and descending order, right? If you remember. Okay, so let us take the same thing. So here let us think that the person is climbing the mountain. So how does he climb initially? So initially here the slope is little less. So he can take larger steps. Okay, so slowly he has to decrease his step size. As he reaches to the top of the mountain where the slope is very high, he has to take tiny steps, right? Baby steps he has to take so that he will not fall. Carefully he will be climbing. So now, after reaching this point, let us think that he is getting down. So, how should be his step size? So, here, when the slope of the mountain is very high, again he has to take baby steps only. And then, as he approaches to the bottom of the mountain, he can take larger steps, right? So, to the gradient, when you are applying the part of this ascending, so that we call as gradient ascent. Okay, so climbing down the mountain is nothing but our gradient descent, the change in the step size. So this we take as gradient. That is what measured by our gradient. Since it is the descending problem, we are calling it as gradient descent. So the same thing, you can just see from the top view of the mountain. From the top view, I can see only the top part, right? So which I can see as a dot. Okay, so I just represented that as a circle here. So in the ascending problem, what is happening from x0 to x1? So there is a larger step size, x1 to x2. So the step size is decreased a little bit. Then x2 to x3, little more decrease in the step size, and x3 to x4, little more decrease. So the same thing will happen in the other direction also. Initially, the step size will be very small, and then little more, and then even more, and the step size will be even more. So like this, slowly he'll get done. So this part we are interested. Okay, we are interested in the descending part. So with this illustration, I hope you can get into the concept. Okay, so let's get into the original concept. So this is what gradient descent concept is. Okay, so here you can see a ball. So this is the ball that we are observing. So this ball, let us think that this ball is rolling down. Instead of a person getting down from the mountain, now we are changing the problem statement to a ball rolling here. So here this is the initial position it started, and here you can see this is the gradient or the measure of the step size that we are taking. And slowly the incremental step size is reducing. Okay, so now if you observe when this ball reaches to the bottom, so relatively here there is this curve is little flat. Okay, so this is the parabolic shape basically if you observe. So here it is little flat. Okay, so now when this is the initial weight, what is the output? So it is measured like this on the y-axis. So here on the x-axis, we are taking the weight. On the y-axis, we are taking the cost. Okay, so this is the cost on the y-axis. Next, when the step size is this much, and this is the cost that we have. So like that, at each point, we will be measuring the cost also. So now what is the slope is? The slope is nothing but the derivative of the cost. So how will we be measuring the step sizes? By applying a derivative on the output, right? So this is what we are obtaining. Okay, so this is the task that has happened now. So now let us try to form an equation for the situation that we studied. Okay, so this is the equation. So here B is the next position of our climber or the position of the ball, or let us call this as the output. And A is the initial weights or the input that we have applied. Eta is the learning rate. And delta F of A. So this is our gradient. And here, if you see this minus sign, okay, the problem is gradient descent coming down from the mountain. And this is a minimization problem. We always want to minimize our error. We doesn't want a larger error, right? Always we want to reduce the error or minimize the error. So only we are taking a negative sign here. So and here the eta is the learning factor or the learning rate, and this delta FA is the gradient term, which will give us the direction of the steepest descent. It will not only give us the value or the amount by which there will be a change in the output, but it will also give us the direction also. So now let us take a function. Let us try to understand this with the help of this function. Our output function is defined as f of x is equals to x square minus 2x minus 3. So here x is a real number. So now if I apply partial derivative on this, so then what will happen? Value of the constant will become 0, x square will become 2x, and 2x will become minus 2. So this is what my delta fx is. So now what I want my problem to be a minimization problem. So I will equate this to 0. So when I equate this equation to 0, what will be my x value? So it is 2 by 2, which is equals to 1. So now let us substitute this delta f of x value. We got x value, right? So let us substitute in the output function. So it is 1 minus 2 minus 3. So my output is minus 4. So this is how the change in the output is observed. So when your input value or the weight is 1, so then the output is minus 4. So like this, we keep on performing the partial derivative until we reach to a local minimum. So that is this bottom part. So until we reach here, until we reach to some point, so we will be performing this gradient descent. So here I have taken only x to the power of 2. So only one step we are able to perform. If you take a larger value, so the same process we will be repeating for more number of steps. So from this, what can we say? So now we are trying to search the hypothesis space of possible weight vectors to find the weights that best fit the training examples. Okay, so we are not simply finding the weights, but we are trying to find weights which are best fitting the training examples. So, and this is the basis for back propagation algorithm in multi-layer perceptron. So without this gradient descent, the back propagation algorithm we cannot implement. So it is like part of this back propagation. And it can also serve as the basis for learning algorithms that must search through hypothesis space containing many types of continuously parameterized hypotheses. In our case, the input values, the weight vectors are keep on changing continuously, right? Here, we are considering training an unthresholded perceptron, that is a linear unit only we are taking, where we are measuring the output as O, which we can give as O of X is nothing but the weight vector Wx multiplied with the input vector, that is X bar. So in this case, the training error of a hypothesis or the weight vector is given as E of W is half sigma TD minus OD. So this is the error value, right? But here we will take a square of this. And here your D value is ranging from D to capital D, where capital D is the set of instances. So here D is the set of training examples. TD is the target output. OD is the output of the linear unit. And in simple terms, what we can say, here the error is nothing but half the sum of the squared errors. Okay, half the sum of the squared errors. So this we will be studying in more detail in the next session, and also we will see the derivative of this gradient descent also, how to derive this gradient descent, how to perform also we will see. Hope you enjoyed this video. I hope the concept of gradient descent is clear to you, how we are measuring the error and all. If you have any queries, please let me know in the chat box. If you like the content, please do like, share and subscribe also. Thanks for watching.